Okay, good morning. I want to thank you for the invitation to talk, and I want to apologize for not being able to be in person because of some other obligations. I'm flying to a conference in South Africa in a few hours. I would like to talk about some recent work that we did with Raúl Jiménez from Barcelona on primordial black holes and graviton cosmological background. Before I begin the talk, I want to have this advertisement of an open postdoc positions in my ERC grant, so my recent grant. So if you are interested, or if you have a student that might be interested, please be in touch with me. And now, the work that I will be composed of two parts. The first one will be about evaporation of black holes at the early universe. Now, after we finished this work, we discovered that there was some earlier, or not very recent, but not very old, very recent similar ideas. So in fact, to some extent, this will be a review talk rather than mostly original research, but there will be some new aspect that I will focus here, which are not addressed in the literature. And I've chosen to go ahead with this in spite of this fact, because I found that this topic is so exciting and amusing that it really worth exposing to the larger community, and maybe you'll have your own ideas how to expand it. Now, we all know the relation between omega of radiation and of dark matter, or matter in general. If we have matter, then the matter density goes like 1/1 plus z cubed, while the radiation go like 1/1 plus z to the 4. So this is something that we teach our students in the first classes of cosmology. And this means that the omega of dark matter increases as the redshift decreases, and eventually we go from radiation-dominated to matter-dominated universe. So this is what we see here is the classical picture of a universe, which is early on it is radiation-dominated, and then dark matter, omega of dark, this is omega here. So dark matter increases, omega of dark diffraction, then there is matter radiation equality, which is around z equal 10 to the 4. And then we are now in matter-dominated era. And later on, we'll switch to dark energy or cosmological constant dominated, but this is not interesting for us because we are interested here in the early universe. So this is true for every kind of dark matter, or for matter, not just dark or not dark, this relationship. And in particular, it will be true if we have a population of black holes. So if we have a population of black holes, the density of the relative density of the black holes will go like 1 plus z cubed, 1/1 plus z cubed, while the energy density of the background radiation field will go as 1/1 plus z to the 4th power. So basically we get that the omega of black holes will increase when the redshift is decreasing. So we get some initial fraction of the universe in black holes, and this, in terms of matter, of energy density, this fraction increases with time. So we expect something like this, that if we have a black hole here, black holes, then the relative omega of the black hole increases, but it will not increase indefinitely because the black holes will evaporate if they are small enough. And this figure is from Hooper and al. We are the first to discuss this phenomenon as far as I know. So the black hole will evaporate, and suddenly the energy density of these black holes will disappear, will go to zero because they converted all their energy to radiation. And here, in this case, the universe remained radiation dominated all the time. But the situation can be even more dramatic. A more dramatic situation is this. The energy density or omega of the black holes may increase so much that it may become the dominant component of the universe for some time. So we have this dominant component of the universe as black holes. So we are here in matter-dominated era, but this matter-dominated era is dominated by, not by regular matter, by black holes. And now, if this was, we cannot have it with regular matter, because if it was regular matter, it will continue to be matter-dominated forever. But here, because we have these are black holes, when we reach the age of the universe, reach the time that these black holes have to evaporate, then they all evaporate, and we return back to radiation-dominated era. So this changes the picture of our picture of cosmological evolution of early radiation-dominated era and then matter-dominated era to have now radiation-dominated, black hole-dominated, and again radiation-dominated. So this is the conclusion so far, that there could have been a primordial black hole-dominated era in the early universe, after which, after the black hole evaporated, the universe returns almost, and this almost is very important because the focus on this talk is on this almost, to its usual evolution, and we go back to radiation-dominated era, and we don't, and then to matter-dominated, and so on. So this is the picture that we can imagine here. This is the new picture that we can imagine here. Okay. So what is the masses of these black holes that are relevant? These black holes cannot be too large because then they will not evaporate in time. We want them to evaporate before matter-dominated era. And they will not, cannot be too small because of other considerations, because then they'll evaporate. Everything will happen too quickly and they won't have a chance to dominate. So in terms of the formation temperature, and this is 10 to the 16 GeV, reflecting basically the idea of just after inflation, and here is 10 to the 10 GeV. You'll see later why I don't go down below this 10 to the 10 GeV. So this is the relevant masses of the black hole, which are very easy to calculate because the mass of the black hole, the relevant mass of the black hole, is simply the horizon size at the time. The thing that can collapse to form a black hole must be of the horizon size. So by comparing the horizon size to the local temperature of the universe, I can get we can get the mass, and these masses are from 10 to the 2 to 10 to the 12 grams, roughly speaking, give or take from the mass of a frog to a mass of a blue whale, something like this. Actually, this is slightly larger than a blue whale, but it's an order of magnitude of what we are talking about. So these are very small masses on astrophysical scale, which is important to remember. So they're really tiny black holes. Sort of amusingly, the most relevant scale is about 10 to the 5 grams, which is about human size. We usually don't use are not used to talk about this kind of sizes of black holes. Now, the next question is, for these masses, what is the temperature of the universe at the time that they evaporate? And this can be calculated very simply because the mass dictates the lifetime, and the lifetime is the age of the universe. And once I know the age of the universe, I know the temperature. So this black hole mass dictates the evaporation time, or in other words, the formation temperature dictates also the evaporation temperature. And this is this relationship. the evaporation temperature, by the evaporation temperature, I mean here the temperature of the universe at the time of the evaporation. So this is the temperature of the universe, and I'm pointing here two relevant temperatures. One is the matter radiation equality, which is around here, and this is the Big Bang nucleosynthesis, which is around here. And now you understand why I've chosen the x-axis to be like this, because this is the relevant times for evaporation. We want the universe to be in radiation-dominated era. From here on, it is matter-dominated era, so these arguments will not work. And so this is why we are talking about formation from 10 to the, it could be actually above 10 to the 16, depends on where inflation ends, but this is the usual story that inflation ends at 10 to the 16 to about 10 to the 11 GeV. So this is very early formation time corresponding to this range of evaporation temperature and evaporation times. Now, the amazing thing, and this is the most amazing, that we have here a huge amplification factor, and this amplification factor arises because of this interplay between the time of the evaporation and the temperature of evaporation and the temperature of formation. The ratio between the omega of black hole at formation to omega of black hole at evaporation is inverse to the ratio of the evaporation temperature to the formation temperature. And this is this ratio. This is just taken from the previous figure that I plotted. This is this ratio for different evaporation temperatures. And you see that this ratio goes from something like 10 to the minus 12 to 10 to the minus 19. So this means that a very tiny fraction of the black hole at a very early universe, 10 to the minus 18 of the, if 10 to the minus 18 of the black holes of the universe at the early time forms black holes, then this will be sufficient for these black holes to dominate later on. It's a remarkably small number, which is amazing. And this means that to get to this picture, you don't have to produce many black holes. You have to produce minute amount of black holes. 1 in 10 to the 18 horizons have to collapse to a black hole in order to later on that the universe will be dominated. By the way, this point here is a very interesting, this last point here. This is the more or less matter radiation dominant equality. And this means that if we are talking about higher mass black holes, so far I was talking about small mass black holes. This limit here of about 10 to the minus 19 is also relevant for higher mass black holes. Take any mass of black hole that you want to consider in any scenario. If more than 10 to the minus 19 of the universe may be produced by these black holes, this may give you troubles later. Okay. So what is even more amazing in this scenario is the following. That in this scenario, that the universe is dominated by black hole, everything after the evaporation of the black hole, almost everything, is made of this debris of the black hole evaporation, the thing that resulted from black hole evaporation. So this completely changes our picture of matter in the universe now. We are used to say in popular talks that we are all stardust, that all the atoms in us were once inside stars and they were processed inside stars and synthesized in stars. So the oxygen and the iron that is in our body is because our body was, or the atoms of our body were once in stars. But in this scenario, the situation is even more dramatic. In this scenario, we were all inside black hole once. And we were all inside black holes, and the black holes evaporated and turned out some regular matter out of them. And so we, in this scenario, we are not, we were first inside black holes, and then inside stars, and then we became humans. So this is even more exciting. Okay, so this is why I got very excited when I realized this idea. Now, and a second question that one can ask here is, what is the evaporation temperature? And there are two temperatures here. One is the temperature of the universe at the time of the evaporation that we discussed. This is this temperature. But the second temperature is the temperature of the evaporating black holes, which is different. This is the temperature in which typically the black hole emits most of its mass. And it is easy calculation to find it, because once you know the mass, you know what is the typical evaporation temperature. And you find that the evaporation temperature of the black hole is typically orders of magnitude larger than the temperature of the universe at that time. This will be very interesting and very relevant to the next question that we discuss: what is the composition of the universe? So what is the composition of the universe? What is the evaporation product? The evaporation product depends now on the temperature of the evaporating black holes. And this is from the Planck collaboration, but this is the standard figure of the number of degrees of freedom. So as you go here to higher energies on the right, you have more and more types of particles. So the total G star weight increases up to, and at least the standard model stops at about 106. And if you go to lower temperatures, then we get also only the regular particles. And eventually, when you go to very low temperatures, below the electron rest mass, you get only photons and neutrinos and gravitons. This is one of the only processes in the universe that can produce high energy gravitons and relatively high energy gravitons of few electron volts up to few keV. And this is what happens here. So at low temperatures, we have only gravitons and neutrino, and possibly also unique type of dark matter, which remains here. And also at high temperature evaporates less gravitons and less neutrinos. Now, what is the fate of these particles? Typically, if the temperature of the evaporation is above the weak interaction temperature, or which is about the black body. By weak interaction temperature, I mean here something very specific, the temperature in which neutrinos are decoupled. And this is the neutrino decoupling here at around 1 MeV. So if the temperature is above 1 MeV, then the only thing that remains from this is gravitons. Because the universe will be opaque to all these particles, and all these particles will immediately thermalize and combine with the rest of the universe, and we will not have remnants here. There is one exception, which I will mention later, the special type of dark matter. If the temperature is below this temperature in which neutrino decoupling, then neutrinos may also recover. And you can see from here, the fraction of gravitons is less than about 1% if the temperature is high, and gravitons and neutrinos together are less than about 3% if the temperature is low. So as I mentioned already, only gravitons are formed if the temperature is weak. And the evaporation temperature of the temperature of these gravitons here I measure it in degrees Kelvin, range from about 10 to the 7 to 10 to the 4. So these temperatures are, in other units, are from about few keV to, 10 to the 7 to 10 to the 10. So there are few keV to few MeV. This is a unique range of gravitons temperature. By some coincidence, it is a similar range to the range of gravitons that are produced by collisions in the sun, by proton-proton and proton-electron collisions in the sun, kind of gravitational Bremsstrahlung, produce also radiation of gravitons. The sun is emitting about 10 to the 17 ergs per second in gravitons of comparable temperatures. But if this is relevant, then this background field of graviton will be much stronger. As I said, if the temperature is low, then the neutrinos will also survive. They will not be coupled to the neighborhood, and in this case, we'll have more of these light particles, light relics. So this is, here you form only gravitons, here you form gravitons and neutrinos. Now, there is also another exciting possibility. If there is a particle of X, I don't know what is this particle, that satisfies the following condition, that the cross-section of X with X bar times the number density of these particles times C over H, this is the relevant time, is less than 1. This is the cross-section for the annihilation, the chance for the annihilation. If this is less than 1, this particle could be dark matter. Now, in the usual scenario, which is called the WIMP miracle, the H here is related to the mass of the particle. Now, the H here is related to the time that the black hole are evaporating, and this has nothing to do with the mass of the particle. So here, this is a way to produce dark matter that doesn't satisfy the usual freeze-out relation, the relation which is called the WIMP miracle. So this is also very interesting. This is very interesting by itself, because this this is a way to produce dark matter that avoid this classical band in which we are typically looking for dark matter. So this will be dark matter that will be found with a cross-section for annihilation and mass that do not satisfy the usual relationship for these particles. Now, you may say, okay, you have all this evaporation, you have all these events. Will they induce structure in the universe? Because here the black hole evaporated, but next to it, black hole did not evaporate, will it produce structure? So we calculated the distance between the evaporating black holes and compared it to the horizon size. And you see that the distance between the evaporating black holes is minute compared to the horizon size. This means that within every horizon, there will be so many of them that this distance between them will be so small that there will be no structure formation because of this phenomenon. Another effect, can we see this explosion, remnant of explosion? So this is a story for another talk. Black holes don't explode, they just evaporate quietly without interacting between the different particles. And you can see this because the cross-section, even if you take a typical electromagnetic cross-section, like the Thomson cross-section, the cross-section for times the relative density is smaller than 1 for all black holes which are less than 10 to the 4 grams. So this means that the black hole just evaporate and don't explode, so there is no explosive signature of this event. So summary up to here, a tiny fraction of of the universe in black holes at very early time can lead to omega black holes of order unity to black hole dominated era later. As this black hole evaporate, universe return to the radiation dominated era, and they return almost all their mass to regular radiation. The exceptions is really gravitons, which don't exist in other scenario, in the usual radiation dominated scenario at this level, and possibly extra type of neutrinos, not type in the sense that these neutrinos will have different kind of neutrinos. There will be the regular neutrinos, but they'll have much different, very different energies, much higher energies than the energies of the regular CMB neutrinos. The regular, not CMB, the regular neutrino background, which is about 1.7 degrees. So these neutrinos will have temperatures of energies of about a few keV or even more. So there will be, in this sense, there are different types of neutrinos. And as I said, that this can also produce dark matter. Okay, can it have other effects on the universe? So a possible effect is on the Hubble tension, which you know very well. This is the early universe measurement from the CMB time. And this is the late universe measurement from supernova. And there is this growing tension, which began as a small tension, but now it's getting to 5 sigma or something like this between the early and the late universe. This may be influenced by the effect that we discussed so far, because the solution of the tension is to increase the acceleration of the universe's early time by about 5%. And if you do this by adding about 5% to the right-hand side of Friedman equation, by adding something more there, this will change the ruler of the reconnection, and this will explain why we have this difference here. The idea of doing this with radiation is not new. It is called dark radiation. We have dark matter, we have dark energy, so why not have dark radiation also? Dark radiation is radiation that cannot be observed otherwise. Gravitons are perfect type of dark radiation, and neutrinos to some extent are also dark radiation. So gravitons, these gravitons and neutrinos that we discussed can do the job. And in fact, this is considered the simplest solution to the Hubble tension, that there exists an additional field. This field is important only at the early universe because of the regular phenomena that the radiation and the energy density of the radiation become insignificant later on in the matter and the cosmological constant dominated era. So it becomes irrelevant and we can forget about it. So did we find the dark radiation? Difficult question. The one way to characterize the dark radiation is to use it by N effective. N effective is the number of that invented in the early days of nucleosynthesis, of Big Bang nucleosynthesis, as a way to measure the effective number of degrees of freedom apart from photons at the time of Big Bang nucleosynthesis. The number due to neutrinos is 3.044. It's not exactly 3 because of the way neutrino decouples from the rest of the universe, so there is some small correction. And to this we can have delta N effective, extra degrees of freedom. And this extra degrees of freedom that people were thinking about for first or fourth, different type of neutrino, or now this dark radiation. And because of this relationship, if omega of dark radiation is about 1%, then delta N effective corresponding one will be about 0.026. So can we add 5% of gravitons and neutrinos to the dark radiation and forget this question? This is difficult. This is difficult because depending on when the evaporation takes place, if it's too early, there is not enough graviton. However, there is enough neutrinos if the evaporation is late. So this means that, well, you have to look at the details of the situation. It is not so simple. Why there are fewer neutrinos than graviton? Graviton are S equal 2. And if you look at Schwarzschild black hole, then the amount of energy that goes in graviton is suppressed compared to the number of energy that goes to the energy that goes in neutrinos. Most of the energy comes in neutrinos. So this is too bad because we want the gravitons. We don't care about the photons. This is a loss. And we don't care about the neutrinos if the evaporation is, at least if then the evaporation is early. So we want to be here, but there is this 2 orders of magnitude suppression. However, this was some earlier work by Page for a Schwarzschild black hole. If we go to a rotating black hole.
You've got about 5 minutes.
Yeah, okay, thank you. If you go to a rotating black hole, then this increases and now gravitons become dominant. So we may say, okay, we may save the day by rotating by rotating black holes. This will complicate the situation because you will need to impose now that these black holes are rotating. But then you talk with people doing working on Hubble tension, and they tell you the dark radiation is completely ruled out. And it's ruled out because of limits on delta n, and this limits, this is from Schoenberg et al. From a paper called Hubble Tension Olympics. So this Hubble Tension Olympics put this limit here, and or delta m. So where's delta n here? The important is that it doesn't allow you to go far enough. And this is because of silk dumping. The dark radiation, when it gets out the potential wells of the dark matter, streams out, reduce the potential well, and the CMB gets a very strong limit on this. So we say, well, this was a nice story, but it is completely ruled out. It is not so obvious because what is not obvious is that maybe the gravitons that we are talking, the neutrinos that we are talking about can avoid silk dumping. If they can avoid the silk dumping somehow because they are more, this field is more uniform than others, this is a question that has to be explored, then this is the same figure without silk dumping, and you can see now that the observational limits are are very different, and you can go to much higher and effective, and you can easily resolve the tension. So there is a question here about more detailed question about how things work. So, but this is not the end of the story because we can reverse the argument. The cosmological observation that I'm discussing here are improving all the time for other reasons. I mean, cosmologists are really interested in these questions, and there is a lot of effort to find more and more details about the CMB and other things like the baryonic BAO and so on at this stage. So these observations will give us upper limit. And it may very well that they will rule out the existence of this gravitons field or put very strong limit on this graviton field and neutrino field. Now, if this puts stronger limit on the graviton field, this means that we can rule out put an extremely strong upper limit on primordial black holes at masses less than 10 to the 12 grams by extrapolation, and maybe even by extrapolation to higher mass. For example, evaporation of 10 to the 12 to 10 to the 15 in this range may dominate the CMB and produce observable effect on the CMB, because there will be significant amount of radiation in this energy band. Okay, this was really the first part of my talk. I needed another 5 or 10 minutes to discuss another solution to Hubble tension by Planckian gravitons. I'll just mention 2 words on the idea. It is possible, not it is possible. During the Planck era, you can have a process that X plus X bar goes to graviton plus gravitons, to 2 gravitons. And the cross section for this goes like the gravitational radius squared at energy E. And if you look at this, you take this cross section multiplied by the density of particles by the time, and put here instead of energy the Planck time, you get 1. This means that omega graviton can be produced by annihilation. It's gravitons which are produced simply by annihilation, just like E plus plus E minus goes to 2 photons. You have here E plus plus E minus go to 2 gravitons at a significant, very significant amount of order unity. So this produces an early, very early Planckian graviton background. And the question now is how strong it is, because this background is washed out by inflation, but some of it can produce just after inflation if the end of inflation is not too low. So this may be another source of background gravitational field, but I don't have time to discuss it now, so I will stop here. And this is the summary. And again, I'll summarize with this amazing fact that we can have a primordial black hole dominated phase in the early universe, even if the initial fraction of black holes that formed was very small. And these black holes will disappear if they evaporate, returning to radiation dominated era, leaving almost no sign of them, apart from this graviton background field, which we should look for, and we may even discover one day. And I'll stop here. Thank you.